Hi, this is a video presentation of our ML final project called BeatBuddy, which is a song popularity predictor and a music recommender system. So, in recent years, we have become accustomed to using phrases like play songs like Girls Like You on Spotify or play today's hit songs when interacting with music software products. These phrases are made possible by recommender and ranking systems, which are the core algorithms powering them. Almost every music software product we use relies on these systems to provide us with a more enjoyable music experience. The popularity of certain songs can be attributed to their shared musical attributes. These attributes can be used by systems and artists to predict whether a new song conforms to them and will be a hit. Music recommendation systems work by analyzing a user's music preferences and suggesting a song that is closest to their preference. Some models use collaborative filtering on audio properties of the song, while others cluster similar songs together and recommend new songs from the cluster. For this project, we will be using the million song dataset, which includes 1 million songs and 300 GB of metadata. The dataset includes features such as beat frequency, artist tags, energy, etc. Although we may not know what each feature represents in terms of audio properties, we can use these features to engineer more meaningful features for our model. The objective of this project is to create a music system that can analyze a song and predict its potential to become a hit in the market. Additionally, we aim to build a recommendation system that can suggest similar songs to a given song. To achieve these objectives, we plan to build and compare both supervised and unsupervised machine learning algorithms. Supervised algorithms will be used to predict whether a song has the potential to become a hit or not based on its features. On the other hand, unsupervised algorithms will be used to cluster similar songs together to provide recommendations when given an input song. By comparing the performance of these algorithms, we hope to gain insights into their strengths and weaknesses. Our ultimate goal is to create a music system that can accurately predict the popularity of songs and provide relevant recommendation to users. So this is an overview of our ML pipeline. We have the million song dataset. We'll use it to extract feature correlations and then use these feature correlations to design unsupervised learning models and also supervised learning models. In this case, the unsupervised learning models will be for the music recommender system. So now let's go over the data collection. The first phase of data collection involved obtaining data from the million song dataset. The dataset is available as an Amazon public dataset snapshot. We attached this to an EC2 instance to obtain the data. We used 37 GB out of the almost 500 GB of available data, resulting in about 137,000 songs for our analysis. The data has 54 features in total and doesn't include any audio, but it does provide a summary file which we use to get the data type of each column. In the second phase, we clean the data by removing list-like features and eliminating about 71,000 NaN values. This left us with 24 features. We use these to generate a correlation matrix, which can be seen here, and we dropped the highly correlated features. This heat map shows that danceability and energy values are 0 throughout the dataset. An external API is required to fill these values. For this project, we didn't use these features. We also dropped all non-numerical values and records that had null values or year values set to 0. This left us with about 41,000 records and 24 features. Out of the 24 features, we kept 19 of the most independent features for predicting a song's popularity score. These features are listed here. And this is the correlation matrix for the 20 most independent features in the dataset. And this final table, it shows the feature description of our final dataset. Now let's go over the methodology. So in this section of our project, we explore the methods we use to analyze our music dataset. We started with an exploratory data analysis, which is an EDA, to understand the spread of artists across the world and the propagation of various music genres across different regions. However, we observed that the genre feature in the dataset was reductive in its tagging of artists, and we decided to use the latent dielectric allocation algorithm to create soft clusters of genres for each artist. We refer to this soft clustering of genres as the branding of an artist. Our first goal was to predict the hotness of a song, which is a direct indicator of its popularity. To achieve this, we implemented 5 supervised learning algorithms and evaluated their performance using 2 evaluation scores: the coefficient of determination R2 and mean squared error, as well as accuracy, precision, recall, and F1 scores. We also performed feature selection from the previous section to improve our model's accuracy. For the classification model, we binned the data on song hotness score in intervals of 0.25. The following graph shows the distribution of hotness scores, which is highly imbalanced due to most of the scores falling between 0.25 and 0.75. A second goal is to recommend similar songs to users. We used unsupervised learning algorithms to cluster songs with similar attributes and provide recommendations to users. We used the k-means and dbScan clustering algorithms and selected 10 features based on their ability to uniquely identify different music attributes of the song. These 10 features are listed here. Now let's go over the results and discussion. So the first visualization plots the location of the artists on a folium map using their latitude and longitudinal features. This was just to see the spread of the artists in our dataset. Next, we plotted a histogram to show the distribution of song releases over the years, which can be seen to be skewed towards the 1990s because most of the songs in our dataset come from that era. To categorize the genre of artists, we used LDA as described earlier on the artist terms and artist term weights features of the dataset to bin the artist into 10 different brandings. The terms associated with each branding can be seen in this table. We then plotted the resulting genres in a histogram to show their distribution in our dataset. To explore the relationship between the song and artist hotness, a joint distribution plot was created between the two variables. The contour plot showed that artist hotness is positively correlated with song hotness for all genres. We then created an interactive visualization to depict the propagation and popularity of brandings of 4 out of the 10 genres categorized over the years. So, for example, for this one, we can see how the metal genre has progressed in its spread across the world over the years. Then we conducted PCA on the segment timbre features to distinguish between genres. The following graph shows the results between metal and rap genres, and a clear distinction can be seen between the two. We also projected a T-distributed stochastic neighbor embedding to visualize all the 10 genres, and the distinction between the genres is quite apparent. The performance matrix for the two models were calculated, linear regression and random forest regressor. The random forest regressor model had better performance matrix than the linear regression model. The difference between the MAC scores and the R2 scores for the train and test data is not very high for linear regression, which means that the model is not overfitting. But the low MAC score is not supported by the high R2 score, which indicates a poor model. We aim to improve this by increasing the size of the data. This is the feature importance score for the random forest regressor that showed that artist familiarity and artist hotness had the highest importance scores among the selected features. This suggests that an artist's brand plays a big role in determining the popularity of a song. During the analysis of the k-means algorithm, we ran the elbow method analysis over a range of k values from 1 to 40. The elbow plot indicated that the elbow formed over cluster number 10, after which it became stable and flatlined. This is an acceptable number of clusters and also conforms to our findings from the EDA. We observed the data to be broadly split between 10 genres, so identifying 10 clusters through the elbow method seems to be an intuitive result. To evaluate the performance of both k-means and dbScan algorithms, we calculated the silhouette score. For k-means, we obtained a silhouette score of 0.3018, while for dbScan, it was 0.1604. We display a few examples for both k-means and dbScan. And in conclusion, during our project, we encountered dirty data and realized the importance of feature engineering. We found that having impactful features can compensate for a decrease in data points, leading to better model performance. Exploratory data analysis helped us understand the characteristics of different features in our dataset, and we were able to identify common features between songs that were more descriptive than their genre. Moving to the supervised learning, we were able to classify songs with potential to be hot using the million song dataset. We also extracted significant features from the dataset that contributed towards our model's decision making. In the unsupervised learning domain, we used LDA to group songs with similar associated terms into identical brandings. We also employed the k-means and dbScan algorithms to recommend similar songs to a particular song based on their features. Our framework and pipeline can extract songs of similar branding and recommend similar songs to a particular song.